Welcome to the deep dive. We take your pile of sources, pull out the absolute must-know info, and basically give you that shortcut to being genuinely well-informed.
And today, we're diving deep into one of Earth's really big players, the Cascadia subduction zone. It's a name that, usually makes people think instantly of huge earthquake risks, tsunamis, the whole 9 yards for the Pacific Northwest.
Right. For years, decades even, Cascadia has been all about the threat of what's coming.
Mm-hmm.
But this deep dive, it's actually about what's ending.
Yeah, it's fascinating. Scientists have managed to catch a subduction zone, one of these enormous geological engines that literally move continents and recycle the planet's crust. They've caught one in the act of dying.
Which is just unprecedented, right? To see it happening.
Absolutely. So our mission today is to really get into the weeds of this geological mystery. How do these massive tectonic engines actually shut down? We're zooming in on the Juan de Fuca and the Explorer plates just off Vancouver Island.
And the sources we've looked at, they offer this incredible window into something that, until now, was mostly just theory. It's a mechanism that might just solve some long-standing puzzles in geology.
It's a really fundamental question, too. These subduction zones are driven by truly immense forces. You've got this dense oceanic crust sinking down, pulling everything behind it. It seems almost unstoppable.
So the big question, the one researchers have wrestled with for ages is, what could possibly cause such a powerful system to finally, give up, to just stop?
It's a critical question because if they never stopped, well, think about it. Continents would just keep crashing together. Eventually, you'd end up with one giant supercontinent, no more ocean basins opening up.
Earth's whole dynamic surface would grind to a halt. Geologic history just gets wiped clean.
Exactly. So the very fact that our planet is still dynamic, that plates are still moving, tells us there has to be a way for these engines to fail, to terminate.
And the initial thinking, based on the sources, was that this ending must be really dramatic, right? Sudden, a catastrophic event.
Yeah, if you've got this massive slab of rock pulling itself down into the Earth's mantle with incredible force, how do you stop that? It seemed like it would need something equally massive to jam the works.
Like a sudden collision, maybe? Something getting stuck?
That was the sort of hypothesis, something big and immediate to counteract that immense pull.
Which leads us perfectly to this really valid analogy from the lead author of the study, Brandon Chuck. He initially framed it like this. Getting a subduction zone started is like trying to push a train uphill.
Which is hard enough.
Right. Ending it requires something dramatic, basically. A train wreck. That was the mindset.
But what they actually found is that, well, it's much stranger and maybe even more interesting than a big crash. It's this slow, almost agonizing step-by-step shutdown.
A tectonic engine just falling apart.
Okay, so before we watch this engine die, maybe we should quickly unpack what it actually is. Why do we call these subduction zones colossal engines?
Good idea. Lay out the basics for us. What's happening mechanically?
Well, at its core, a subduction zone is where one tectonic plate dives, or subducts, beneath another one, sinking down into the mantle. Simple enough on the surface.
But the engine part comes from the power source. Right?
Exactly. The real driving force isn't something pushing from behind. It's called slab pull. It's fundamentally gravity doing its thing.
So explain slab pull a bit more.
Okay, so oceanic crust forms at mid-ocean ridges. It's hot and buoyant. But as it moves away over millions of years, it cools down. And as it cools, it gets denser, heavier.
Right. Colder rock is denser rock.
Precisely. So when this old, cold, dense edge of the plate reaches a subduction zone, it starts to sink under its own weight. And that sinking slab literally pulls the rest of the plate along behind it.
Like an anchor dragging a chain.
That's a good way to think of it. And this gravity-driven pull is powerful enough to move entire continents across the planet's surface. Maybe just centimeters or tens of millimeters a year, but over geological time. It reshapes the whole globe.
And these zones aren't just about moving continents around slowly. They're also ground zero for some of the most, violent geological events we know.
Oh, absolutely.
Right.
Megathrust earthquakes, the really big ones, like the potential magnitude 9 big one people worry about in Cascadia, those happen right at the subduction interface.
And the tsunamis that often follow.
Generated by that same sudden movement of the seafloor during the earthquake. Plus, these zones fuel volcanic arcs. Think of the Pacific Ring of Fire.
How does the sinking plate cause volcanoes?
As the slab goes down, it carries water trapped in minerals. Deep down, the heat and pressure squeeze that water out. That water rises into the mantle rock above the slab, and water drastically lowers the melting point of rock.
Ah, so it makes the mantle melt more easily.
Exactly. That molten rock, magma, then rises to the surface and erupts, forming those chains of volcanoes parallel to the trench. And beyond all that drama, subduction is also how the planet recycles its crust. It balances out the new crust being made at mid-ocean ridges.
Okay, so let's bring it back to Cascadia specifically. The plates involved in this deep dive. Which ones are they?
We're looking primarily at the Juan de Fuca plate, the JDF, and a smaller piece next to it called the Explorer plate,
And these are sliding
under the massive North American continental plate. They're actually remnants, smaller pieces left over from a much larger ancient plate called the Farallon plate, which has mostly disappeared beneath North America over tens of millions of years.
So this specific system, the Juan de Fuca subducting under North America, it's been going for a long time.
Oh yeah, roughly 40 million years. So it has built up incredible momentum. That slab pull has been working relentlessly for eons.
Which brings us back to the puzzle. With that much momentum, that powerful gravitational pull, why was it so hard for scientists to model how these things stop? Why did they lean towards that train wreck idea initially?
It really comes down to the physics. That slab pull force, the negative buoyancy of the sinking slab, it's just pervasive. It's constantly acting unless something truly massive gets in the way.
Like trying to stop gravity itself?
Kind of. So scientists looked for things that could physically block it. Maybe a big, buoyant underwater mountain range, or a plateau hitting the trench and refusing to sink, something that could clog the system.
But those kinds of collisions are rare.
Or relatively rare, yeah. And they wouldn't necessarily explain all subduction zone endings. The real paradox was, how could the engine lose its driving force, that slab pull, without some sudden, obvious obstruction? Gravity doesn't just switch off. It felt counterintuitive that it could just fade away.
But it turns out nature had a trick up its sleeve. A way to stop the engine slowly by basically taking it apart from the inside out.
Exactly. They found this mechanism for essentially self-destruction. It relieves the immense stress piece by piece rather than waiting for one single catastrophic failure.
And this mechanism is key, you're saying,
Yeah.
because it allows Earth to keep changing to avoid becoming that static supercontinent.
Precisely. It allows the cycle to continue.
Okay, so that leads us right into how they actually saw this happening.
Yeah.
Section 2. Capturing the moment. If this process takes millions of years, how on Earth do you gather data on it now?
Well, they needed the right location. And the area just off Vancouver Island, where the Juan de Fuca plate meets the Explorer plate, and they both dive under North America, turned out to be the perfect natural laboratory.
Why there specifically?
It seems to be the place where the stresses are currently most concentrated. The signs that the plate is starting to, well, falter are clearest right there. It's like the weakest point in the chain right now.
And to actually see this happening miles below the seabed, they needed some pretty extraordinary technology. Not just listening for earthquakes, but imaging, right?
Exactly. They use a technique called seismic reflection imaging. It's often compared to giving the Earth an ultrasound scan.
An ultrasound, okay, but on a massive scale.
A planetary scale, really. You send powerful sound waves down, and you listen for the echoes bouncing back from different layers of rock beneath the seafloor. And they combine this with really detailed analysis of earthquake data from that specific zone.
I want to pause on the tech for a second because this seems crucial. This wasn't just any old ship pinging the bottom. This was a major dedicated scientific effort, right? The 2021 Cascadia Seismic Imaging Experiment, KC-21.
Oh, absolutely. It was a huge undertaking, funded by the NSF, the National Science Foundation. They used a specialized research vessel, the RV Marcus G. Langseth, which is equipped specifically for this kind of work.
So the ship sends out these powerful sound pulses.
Right. Using arrays of air guns, basically, that release bubbles of compressed air to create the sound waves. Those waves travel down through the water, penetrate the seafloor, and go deep into the crust and even the upper mantle.
And then they bounce off different rock layers, different structures, boundaries between sediment and crust, or crust and mantle, and reflect back up.
Exactly. And the key to getting a detailed picture, especially of deep structures, is how you listen for those reflections.
And that involves something pretty unique, didn't it? This massive streamer.
Yeah, this is where the Langseth's capability really shines. They towed this enormous streamer, basically a cable packed with underwater microphones, or hydrophones, and the streamer was 15 kilometers long.
15 kilometers, that's, what, over 9 miles long? Towed behind a ship.
It's incredible, isn't it? A huge piece of high-tech equipment.
Why does it need to be so long? What does that length give you?
Two critical things: resolution and depth penetration. Think about it. The sound waves travel miles down, they reflect off structures that might be tilted or complex, and the signal gets weaker and spreads out.
Okay.
A really long streamer captures those returning echoes over a very wide area. This wide aperture gives you much better focus, kind of like using a bigger lens on a camera. It allows you to resolve finer details and, crucially, image structures that are dipping steeply downwards.
Like the faults and fractures they were looking for deep within the subducting plate.
Precisely. They needed to see features maybe 5 kilometers or more below the seafloor. Without that long streamer providing that wide aperture, the image would just be too fuzzy. You wouldn't be able to tell if you were looking at a distinct active fault or just some general bending of the rock.
So they blast the sound waves, the 9-mile-long streamer listens carefully, and they crunch all that data together to build up a detailed, almost 3D map of what's down there.
That's the essence of it. Sophisticated computer processing turns those millions of recorded echoes into cross-sectional images of the Earth's interior.
And what did those images show? What was the big reveal?
Well, according to the sources, as soon as they processed the data, it was pretty clear they had captured something really special. The images showed distinct, deep fractures, actual fault lines cutting through the oceanic plate.
So the plate wasn't just bending smoothly downwards anymore.
No, it was visibly breaking, splitting apart under the immense stress. These weren't ancient scars. The data indicated these were active features.
Active now. Like happening as we speak, geologically speaking?
Exactly. It was like getting a live snapshot of the plate hitting its breaking point. The images confirmed that the incredible tension built up by the subduction process, that relentless slab pull, was literally tearing the plate fabric apart.
So they weren't just modeling the death of the engine anymore. They were actually seeing the structural failure that kicks off the whole process.
That's it. They were observing the very beginning of the end for this section of the subduction zone.
Okay, this is where it gets really interesting. We move from the how they saw it to what it means. We started with that dramatic train wreck idea.
Right, the sudden catastrophic stop.
But the data just didn't fit that picture. It forced a major rethink.
Yeah, the central discovery, the real game changer here, is that the termination isn't happening all at once. It's not one big event. As Brandon Shuck revised his analogy, it's not a train wreck, but it's like watching a train slowly derail, one car at a time.
One car at a time. So the plate isn't just failing as a whole unit.
No, it seems to be ripping apart piece by piece. That's the key phrase. It's a fragmented sequential failure.
And the researchers gave this mechanism a name.
They call it episodic, or piecewise termination, which really captures that idea. It happens in distinct episodes, affecting one piece or segment of the plate at a time.
Why is that distinction so important? Episodic versus one big failure.
Because it changes everything about how the forces balance out. If the failure happens only in one specific spot, it relieves the stress locally in that area. But the neighboring sections, they might still be intact, still subducting, still pulling.
Okay, one part breaks off, so let's go, the tension there, but the parts next door keep going for a while.
Exactly. They keep subducting, maybe slowed down a bit because part of the pulling force is gone, but they continue until they reach their own breaking point, maybe millions of years later. It's this incredibly drawn-out, agonizing process for the plate.
So what was the smoking gun in the seismic images? What specific physical evidence convinced them of this tearing, this piecewise failure?
The images were remarkably clear on this. They could trace these massive tears, these faults, slicing right through the oceanic crust, the entire thickness of it.
Not just surface cracks.
No, deep, fundamental breaks. And maybe the most dramatic piece of evidence was observing a huge vertical offset along one of these tiers.
Offset, meaning displacement.
Yeah, where the slab on one side of the tear had dropped down relative to the other side by about 5 kilometers.
5 kilometers, that's huge. 3 miles of vertical drop within what should be a continuous plate.
It represents an incredible amount of sheer stress and movement. It's basically undeniable proof that the structural integrity of the plate is completely gone along that line. It's not just bending anymore, it's broken.
And crucially, they confirmed this is happening now.
Yes. Shuck is quoted saying, "There's a very large fault that's actively breaking the plate." And he added that it's close, but, and this is key, not 100% torn off yet.
So they're literally watching the birth of a brand new boundary within the plate.
In geological slow motion, yes. They're capturing the process mid-tear.
Okay, now how does this happen? What makes it easier for the plate to tear apart in these neat segments? The sources mentioned the existing plate geometry plays a role, these transform boundaries.
Right, so you have the main subduction trench where the plate dives down. But cutting across the Juan de Fuca plate, roughly parallel to the direction it's moving, are these other types of faults called transform boundaries.
And those are where plates slide past each other horizontally,
Mm.
like the San Andreas Fault, but out in the ocean.
Exactly like that. There are zones where there's already a lot of lateral shearing stress, and in this context, they act like, well, like pre-existing weaknesses, almost like perforations or score lines across the plate.
Like the perforations on a sheet of stamps.
That's a great analogy. They act like natural scissors, as the researchers put it. These transform faults are zones of weakness that run perpendicular to the direction the main tear is propagating downwards into the slab.
Okay, so the main tear is happening because of the downward pull trying to rip the plate vertically.
Right. And that tear finds it much easier to rip along one of these pre-weakened transform fault zones than trying to break through solid, unfractured rock.
Ah, so the transform fault provides the path of least resistance for the tear to follow laterally.
Exactly. It allows a whole segment defined by these transform boundaries on its sides to break off more cleanly.
Which leads to the formation of these microplates.
Precisely. That segment, once it fully tears away along the deep fault and is bounded by the transform faults, becomes effectively a separate, smaller plate, a microplate. And while that piece is now detached and may be sinking on its own, the segment right next to it on the other side of the transform fault is still attached to the main Juan de Fuca plate and continues to subduct.
Until its turn comes to tear off along the next transform boundary down the line.
That's the piecewise mechanism in action. The transform faults basically dictate where the segments will break.
Okay, so the seismic images show the tears. What about earthquake data? How does that confirm this story? They talked about a seismic signature of death.
This is really compelling evidence, too. They looked very closely at the pattern of small earthquakes occurring along that massive 75-kilometer-long tear they imaged.
And what did they find?
A really interesting split. Some sections of that tear zone are still seismically active. They're generating small earthquakes, which means the rocks on either side are still locked together, building up stress and occasionally slipping. Standard fault behavior.
Okay, that makes sense for an active fault.
But other sections along that same tear zone were described as eerily quiet. Almost no earthquakes happening there at all.
Quiet in the middle of an active subduction zone along a massive fault. That sounds wrong. Why is silence the key signature here?
Because it tells you the connection is already broken. Think about it. Earthquakes happen when rocks are stuck together by friction. Stress builds up as they try to move, and then they suddenly rupture and slip.
Right, you need that friction, that resistance.
Exactly. So as Shuck explained, once a piece has completely broken off, it no longer produces earthquakes because the rocks aren't stuck together anymore. The two sides are fully separated. There's no more friction holding them back along that segment.
So the silence is the evidence.
Yeah.
It means that part of the plate is already detached. The tear is complete right there.
It's direct seismic confirmation of the piecewise detachment. You see active seismicity where it's still tearing and silence where the tear is finished.
And the ultimate result of all this tearing, piece by piece, segment by segment, is that the whole engine loses power.
That's the long-term consequence. You're essentially removing chunks of the heavy sinking anchor. Slab pull depends on the mass and density of that sinking slab.
So less slab means less pull.
Exactly. As you progressively tear off these microplates, you're reducing the total downward gravitational force that's pulling the rest of the plate along. The engine loses its momentum, slows down, and eventually, over millions of years, the entire subduction system in that region grinds to a halt.
And we really need to stress that time scale again. When we say slow derailment, we're talking geological time. Millions of years for each piece.
Absolutely. This isn't something that affects next week's earthquake forecast directly. We're observing a process where each major tear, each segment breaking away, likely takes several million years to fully complete. But watching it happen now gives us the mechanism for how these things have ended throughout Earth's history.
And that's the perfect transition, because what's so powerful about this Cascadia discovery is how it suddenly illuminates geological mysteries seen all over the world, right? It's like finding the missing instruction manual.
Precisely. Geologists have seen features in the geological record for decades that were puzzling, but this idea of episodic or piecewise termination provides a really elegant explanation for them.
Like what kind of features?
Well, things like abandoned chunks of tectonic plates found far from any active plate boundary, or strange, isolated bursts of volcanic activity occurring way inland, not directly above a currently subducting slab.
And the prime example, the classic case study, involves that huge ancient plate we mentioned earlier, the Farallon plate.
Yes, Yes, the Farallon is the poster child for this. It was this enormous oceanic plate that used to lie east of the Pacific plate. Over the last, say, 100 million years or so, most of it has subducted beneath North America.
But it didn't just vanish neatly.
No, not at all. If you look at the geology and geophysics off the coast of places like California and Baja California, you find these incredibly complex patterns. Scientists identified what they call fossil microplates, small fragmented remnants of the once mighty Farallon plate, just sort of sitting there under the edge of North America.
They knew these were pieces of the dying Farallon plate.
Right. They knew it must have broken up as it died, but the how was the mystery. Why did it shatter into these small pieces instead of just sinking as one coherent slab until the very end? The mechanics were missing.
So Cascadia, by showing this active tearing and segmentation right now, provides the direct observational evidence for how the Farallon likely broke apart.
That's exactly what the sources suggest. The Farallon plate didn't just subduct and disappear, it likely underwent the same process of episodic, piecewise termination. It tore itself apart along transform boundaries and other weaknesses as the subduction process waned, leaving behind those fossil microplates as the evidence.
It wasn't a clean sinking, it was a messy, fragmented collapse.
Exactly. A slow, drawn-out unraveling, section by section, leaving geological wreckage behind. Cascadia gives us the live-action view of how that wreckage is made.
Okay, let's think about the future implications, geologically speaking. When one of these pieces tears off, it does something quite dramatic to the subsurface structure, doesn't it? It creates an opening.
Yes, this leads to a really interesting phenomenon called a slab window. When a segment of that cold, dense, subducting slab completely detaches and sinks down into the deeper mantle, it leaves behind a gap, an opening, a window, in the otherwise continuous descending sheet of lithosphere.
And what happens at that window? What fills the space?
Hot, buoyant rock from the asthenosphere, that's the partially molten layer of the upper mantle below the tectonic plates, wells up rapidly to fill that void.
So hot mantle material rushing up closer to the surface where the cold slab used to be.
Exactly. And this isn't the same mantle material that gets melted above a normal subducting slab by adding water. This is deeper, hotter material rising quickly.
And when hot mantle rises quickly like that,
It undergoes decompression melting.
yeah,
Just like taking the lid off a pressure cooker lowers the boiling point, reducing the pressure on that hot mantle rock causes it to melt extensively, even without adding water.
okay. And that generates magma, leading to volcanoes.
Yes, but often a different kind of volcanic activity than you see in the main volcanic arc, like the Cascades. These slab window volcanoes can pop up further inland, away from the main arc, and they often erupt distinct types of lava, like alkaline basalts that have a different chemical signature reflecting that deeper, drier melting process.
So these tiers deep underground can directly cause seemingly random volcanoes to appear on the surface, potentially hundreds of miles inland.
That's the connection. These slab windows migrate over time as the tier propagates along the plate boundary. You might get a track or a belt of volcanic centers on the surface that marks the path of that migrating tear edge deep below.
And does the geological record support this? Do we see evidence of these migrating volcanic belts?
Absolutely. The researchers specifically noted that this model of progressive, stepwise tearing fits beautifully with the observed patterns in the geological record in some areas. You might see a line of volcanic rocks where the ages get progressively younger or older in one direction, perfectly matching the expected sequence as a tear opens up and the slab window migrates laterally.
So the tearing process is literally rewriting the volcanic landscape over millions of years.
It's all part of that cycle. Plate boundaries move, microplates form, slab windows open and close, volcanism shifts. It's a constantly evolving picture driven by these deep tearing processes.
Okay, critical question time. Let's bring it back to the present day and the people living in the Pacific Northwest. We have this subduction zone that's actively tearing itself apart, slowly dying over millions of years. Does this change the immediate earthquake hazard? Are people safer now?
This is probably the most important takeaway for anyone listening in that region. And the answer, according to the sources, is clear. No, these findings do not significantly change the near-term hazard outlook.
So the big one is still a major concern.
Absolutely. The process of tearing and detachment takes millions of years. On human timescales, decades, centuries. The Juan Fuca plate is still largely locked against the North American plate. It's still building up enormous amounts of stress. The potential for a massive magnitude 9-level megathrust earthquake like the one that occurred in 1700 remains very real. This research doesn't diminish that threat.
Surely, knowing how the plate is structured down there, knowing about these huge tears and segments, must be useful for understanding future earthquakes, even if it doesn't lower the overall risk.
Oh, incredibly useful. This is where the research provides immense value for hazard assessment and mitigation. Before this, models often had to treat the subducting slab as a relatively smooth, continuous surface because we lacked detailed imaging.
But now we know it's not smooth, it's broken, it's got massive tears and faults running through it.
Exactly. We now have high-resolution data on the specific geometry of these deep structures, and seismologists desperately need that kind of detail to build more realistic models of how earthquake ruptures might actually happen.
How does knowing about a deep tear affect how you model an earthquake rupture?
That's the multi-million-dollar question they're working on now. Does a massive tear like the one they imaged act as a barrier? Could it potentially stop an earthquake rupture from propagating further along the fault line?
Which might limit the total area that ruptures and therefore limit the maximum size of the earthquake.
That's one possibility. If the rupture hits that tear and stops, you might get a large earthquake, but perhaps not the full 1,000-kilometer-long rupture that represents the worst-case scenario. It could lead to segmentation of the rupture.
Or could it go the other way? Could these zones of weakness actually help the rupture spread?
That's the other possibility. These complex fault zones might focus stress in certain ways, or provide pathways that allow the rupture to jump or propagate more erratically, perhaps even faster in some sections. We just don't know for sure yet.
But knowing the geometry, knowing where these tiers and potential barriers or conduits are, is absolutely critical for figuring that out.
Precisely. This detailed structural map allows modelers to test these different scenarios. How does rupture behave when it encounters a 5-kilometer offset? How does it interact with these intersecting transform faults? It provides the crucial inputs needed for much more sophisticated and hopefully more accurate hazard modeling.
Which ultimately leads to better building codes, better evacuation plans, better preparedness overall.
That's the goal. So the takeaway for you if you're in the region isn't that the danger is gone. It's that we now have a much clearer, much higher resolution picture of the complex machine beneath your feet that's responsible for that danger.
We've gone from a blurry sketch to a detailed blueprint of the subducting plate's weaknesses.
And better blueprints always lead to better engineering, whether it's buildings or earthquake models.
Okay, let's try and wrap this all up. The real aha moment from this deep dive, the core takeaway, isn't just that they saw a subduction zone dying. It's the fundamental shift in understanding how it happens.
Yeah, it's moving away from that idea of a single dramatic train wreck finale and towards this observed reality of a slow, piecemeal self-destruction, a gradual unraveling.
Episodic termination. The plate tears itself apart, segment by segment, over millions of years.
Driven by its own weight, but facilitated by its own internal weaknesses. It's like the engine contains the seeds of its own demise.
And we're literally watching this happen right now off the coast of Vancouver Island. We're seeing new geological boundaries being born within an old plate. It really makes you think about the Earth not as solid, stable rock, but as this incredibly dynamic, constantly churning and, well, self-dismantling machine.
It really does. And what's maybe even more profound is realizing that this process of death, this tearing apart, is actually essential for keeping the planet geologically alive in the long run.
How so? Why is the death necessary for life, geologically speaking?
Well, think back to that supercontinent idea. If subduction zones just ran forever, pulling everything together, the system would eventually seize up. Continents would merge permanently. Ocean basins, which drive so much of our climate and chemical cycles, would close and disappear.
The planet would become static, geologically dead.
Pretty much. So this mechanism of piecewise termination, of plates breaking apart and allowing new boundaries to form, new spreading centers perhaps to eventually emerge, it prevents that stagnation. It ensures the whole cycle of plate tectonics can continue.
So here's the final thought for you to chew on, connecting this specific tear in Cascadia to the grand scale of the planet. Maybe this process of tectonic death, this messy, slow derailment that creates microplates, open slab windows, fuels weird volcanoes, isn't just an ending. Maybe it's actually Earth's fundamental way of ensuring renewal.
The breaking apart is necessary for new configurations to arise. The death of one plate boundary allows the system to reorganize, to keep moving, to keep the planet's surface dynamic and its history evolving, rather than being erased into one final, static configuration.
Fascinating perspective. Destruction is a prerequisite for continued creation on a planetary scale. Thanks for joining us for the deep dives. We hope you feel thoroughly well informed.